Sí, ya está. Empezamos con Sebastian Arias, que su charla se llama Beyond Try Except, Python's Frontier on Error Handling with Monads and Railway Magic. Un aplauso.
Yep. Well, thank you, everyone. Hello, and thank you for joining me today. I hope you're enjoying so far the conference. And once again, thank you for joining me. And I expect you to have a great time learning a little bit more about monads and functional programming. Well, my name is Sebastian Arias. I am a software engineer at the Stack Builders Consultancy, and I've been a Pythonist for around 7 years, where I mainly have focused on taking all this information and all these functional programming paradigms, concepts, and design patterns to Python for us to use in our everyday tasks. So today we're going to venture beyond the try and accept and explore how monads can elevate how we manage the error handling and how railway programming can help us bring a new perspective on how we structure our code. So I know that you may have heard about these concepts before. It's kind of pretty popular when we start our Python journey. That is, look before you leap, and also easy to ask forgiveness than permission. For the look before you leap approach, basically it checks if something exists before proceeding to our code, if it meets a certain condition or something related in our code. So it's like looking left and right before crossing the street, right? We are double checking that everything is as expected on our code before executing it. So some strengths of this approach is that we have predictable outcomes, right? Because we're handling every edge case. Also, it prevents from exceptions to happen, but it has some trade-offs that we have to take into account. It is very verbose, since we are using conditional statements to double-check that our code has all the inputs that are required as we require them. Also, it tends to have some rate condition issues that, well, you know, are going to mutate the states and make some stuff happen here and there that is harder to debug. On the other hand, we have the easier to ask forgiveness than permission. Basically, it tries to catch any exception that happens in our code, and it's kind of the Pythonic way that Python send explicitly tells us to use, right? To kind of follow the happy path of our code and maybe manage the exceptions elsewhere, right? So some strengths of this is basically that it's the Pythonic way or the optimistic approach of our code to work. Also, it's more concise and meaning less code of writing and maintaining through time because we have a try and accept and we just manage the error that way, right? Also, this way we avoid the race conditions since we're handling all this logic in the try and accept statement. But on the other hand, we have some weaknesses that we have to kind of consider when we are coding our projects. That basically it has lower performance since the try and accept kind of is not that optimized for those situations, or even if we are handling a lot of logic inside those statements, it's going to take extra time to raise the issue once it's inside it. And also it's less explicit, right? Because, you know, we have to throw the exception and catch it in superior layers of our code. So we don't know how it's going to be handled, and maybe we lose context about how the code failed and where it failed specifically because of these rising issues. But at the end of the day, why does this matter on our Python code? Once again, let's go back a little bit to the Zen of Python. We have two kind of statements of the Zen of Python that give us this philosophy that applies not just for our code, but also on how we handle our errors at the end of the day. So when our code is simple and easy to understand, it is easier to maintain, to debug, and extend through time. When our code base grows in complexity, these are some key factors that we need to consider to leverage and also extend our application functionality. So what are some challenges with these traditional approaches of error handling, right? So we've been focusing on these two concepts that are the main way of handling errors on Python. So let's check some things that might have happened on our daily basis or on our projects. First of all, we have scalability issues, right? So when our code base grows in complexity, scaling is one key factor that determines if we can deliver or not some extra features that we might have taken into account. So each check at complexity, and also it makes hard to understand the code that we are doing. The error propagation and error and handling issues is another issue that we encounter when the code base grows, right? So the errors need to be propagated through layers, challenging and changing the context preservation. So we don't know exactly where it happens, but it's recent or logged when we just catch it, right? Another thing is managing null values and some edge cases that might slip through our fingers. So both look before you leap and easier to ask forgiveness than permission struggle with handling null values or unexpected inputs that we might encounter in our code base. And finally, the main factor is readability and maintainability issues. So having clear error handling is crucial for us, right? Because it's the one thing that is going to make us better our application, better our code, and make it more maintainable. And considering this core logic harder to follow, it's going to increment that risk of having bugs in our code base. So this said, we need a more robust strategy to handle errors, right? So we need to help ensure that consistent error handling across our code base. That's one of the main factors that I consider for this. Next, we're going to make it clear when and where the errors occur. So we know the context when the issue is happening. And finally, we want to prevent null variables or even some input that is not what we expected in our code, right? So with proper handling, we can have this information in place. So by adopting this more robust error handling strategy, we can reduce the cognitive load for our code base. So it's going to be straightforward to think what's happening, what we are doing, and just focus in the logic instead of focusing on how to manage these errors, right? For this, I'm going to be introducing you to Monads. So basically, in Monads, Monad is a design pattern that helps us encapsulate calculation, operations, and some other values operations in a consistent and predictable way. That's something that we want in our code base, right? We don't want weird errors or stuff like that. We just want, oops, something happened. Oh, it's back. Sorry about that. Technical issues there. So we are going to have these design patterns that encapsulate our computations and make them predictable. So how we are going to be encapsulating this and how monadic error handling work. Basically, we have 3 steps. Okay. First of all, we encapsulate our operation result. So we grab the outcome of our operation, our logic, our functionality in a monadic value that can be either a success or an error. Then this leverage from this monadic and this result object for chaining operations. So you might be aware of maps, filters, reduce, and concatenation chaining operators this way. So one output becomes the input for the next operation and functionality that we're going to have. So this works under the hood with result monad. And finally, the results becomes predictable. We either have a success or an error. That's basically it. Now, let's see how we can shift these paradigms. The traditional way, we look easy to ask permission and also look before you leap. So how we shift the paradigm introducing the result monad. So basically, a result monad is what I explained earlier on, right? It's a design pattern that encapsulates our operations and makes this predictable with a success or a failure. In this way, we can have a computation that might produce valid operations or might fail with errors. So chaining these operations is easier for us to have a predictable way on how our code works, making this more composable, less prone to null values, less prone to issues about the scalability, and also reducing the cognitive load, just focusing in our logic itself. Yeah, so I found when I was doing this, this is kind of a common idea on computer programming languages like Haskell, Rust, or other functional approaches that have, for example, in Haskell, we have the either monad that give us the success or error. Also, we have in Rust, we have the result monad itself. And this library that I found, that it's called the result library, it's an implementation inspired by the Rust monad of results. Basically, as you can see here, we have our k value, right, that is going to be the success of our operation. And also, we're going to have the error value that represents the failure. All of this is inside a result object that has these two ways. So by using the result library, that is the implementation of the result monad, the feature explained earlier on are going to be unlocked for us. So it's going to just work that way. So what are the benefits of using the result monad and the results library? So basically, we improve the clarity and readability of our code. So we centralize error handling logic within the results object and making it easier for us to understand all of what is happening, where is failing, where is having success, and all these different states that we are going to manage through our code base. Also, we unlocked composability. So basically, we can chain operators, as we normally do, for example, with iterators, with generators, we can leverage from this type of implementations just working out of the box, right? So it's ideal for complex workflows where we need to transform data, maybe run some transformations on next steps and everything, but just in simply one-liners instead of having to have assignations of variables, double-checking that the variable is correct, double-checking that the information that we have is the way that we expect it. Also, we are going to mitigate the null and also the edge cases that might become from unexpected inputs. So handling the success or also the failures through this monad is going to make it easier for us. And finally, consistent error handling. So with consistent error handling, I mean that we are now having just two options, or it's a failure or it's a success, and we can work with that. So how we can adopt this result monad with another paradigm shift that is the railway-driven programming, or as I put it there, is the railway-oriented programming paradigm in functional programming. So basically, you can imagine this as it is, right? Like a railway that a train is going to follow through time. As an example, we have three key concepts for railway-driven programming. So we have the success path. So you can imagine this as the success track that a train is going to follow if everything goes correctly, right? If our operations are going the right way, it's going to follow this track. We have the failure track that is basically where the train or operation is diverted when something happens or something goes wrong. And also, between steps, we are going to have this concept of switching track. So if something fails, it's going to go to the failure track, and if it succeeds, it's going to keep that track there. So enough about theory. Let's jump into some other features in an example that I prepared for you today. Oops. There we go. Let me know if I think I'm going to make this a little bit bigger for you to. There we go. I think now it's visible. So I prepared this example that it's kind of intended to be a little bit more visual. Maybe you can see some patterns there that you might have encountered. It's really, really basic, but I tried to make noticeable of the try except using if statements, kind of doing some stuff that you might encounter in some code reviews and stuff like that, right? So this is basically some type of information that we are going to be validated items, calculating totals, process payments, and as you can see, in every functionality we have the try and accept. If something happens or the information is not as intended, we are going to be raising errors, catching errors, doing some stuff here and there. And basically, when we go to the process order that is going to use these chains of functionality. Okay. Oops. Is this better? Okay, thank you. Well, here in the process order, basically, as you can see, we are kind of having all this concatenation and functionality, right? So we have validated items that is going to collect the items. And as you can see a little bit up here, for example, we have a common pattern that is kind of returning a string for success, that it's the payment is OK, and also a string for error. So we don't know if it's going to be a success string or an error string. And in other processes, as you can see, we're returning, for example, an integer that is the total, and we have a string that is going to be the error. And we have to manage this kind of verbosity on our end, right? So we are checking if, for example, if validated items is an instance of a string object, we know that it's going to be an error string being returned. So it's kind of, we have to infer the type of what we are expecting, right? If that's an error, we know that it's going to be a string. We don't have to do, well, we don't have something out of the box that gives us this cognitive sense or easy to read code, right? So we have to do these kind of things. And also we have a lot of assignation. As you can see, we have validated items that is going to have the value of validated items. We have to check if this validated items is a string. And then if it's a string, we have to raise the error, and we enter in this kind of loop of stuff, right? So we don't strictly know if it's going to be an error, it's going to be a good result. We don't know that, right? So let's see how we can leverage from railway-driven development and results monad, also for refactoring this kind of simple code that I created for you today. So basically, as you can see, right now we forget about the try and accept statements. We just focus on the logic itself. So as you can see, for example, for validated items, we're going to have a result object that the first part of the signatures is the return time of the success track. So for example, we're going to have the list of items, and for the error, we're going to have the string. We just focus on the logic itself. We know if the items is not a list of items, we have to return an error that it's explicit itself saying like invalid items. We don't have value errors, we don't have runtime errors, we don't have any sort of other type of exceptions or errors to handle in try and accept, and maybe making an accept for each of these scenarios and everything. We just know that it failed, and we return an error itself. So the same happens, for example, for return if the quantity is below 0, right? We have another type of error that is going to be an invalid quantity, and we don't have to catch this type of scenarios in a try and accept and handle it in a different way, and etc. And if everything goes right, we're going to be grabbing the result in the OK part of the result object. And the most powerful thing that I encounter when implementing this on Python, so you remember the previous code that we have for the result, we have to be assigning validated items, pass it through another function, double checking if it's an error or it's a valid item. Now pass this value again and again and again. So this makes it straightforward in a one-liner. So we are chaining operations. So in this scenario, as you can see, we have validated items that is going to be receiving the same items, and leveraging from the and then functionality from the result object is going to kind of pipe the output from one function as the input of another, and chaining it together, and it's also easier to read, right? As you can see, is like validate items, and then calculate the total, and then process payment. So we have reduced cognitive load, easy readability, better syntax. We have basically the same functionality that we have before in a one-liner, right? And also, we unlock some new features that Python has provided. For example, pattern matching. Instead of having an if-else clause, if the result is valid, do something else, trigger some kind of error logging or something like that, we can pattern match this. And if it's an OK value, we're going to be returning the result. And if not, if it's an error, we can log it right away, making it explicit. Pattern matching is kind of awesome for this kind of scenarios. So, getting back to the presentation, I have some final takeaways from this result monad on this monadic error handling in my perspective, my experience. So, Since, as we've reviewed in the code example, when adopting the result monad and rate-well-driven development for error handling, the code becomes cleaner and easier to maintain, right? We're just focusing on the logic. We don't have to handle each cases manually. We don't have to be assigning. We unlock also the chaining operator. We have multiple pipes that we can adopt. Also, we can leverage from a more explicit code like pattern matching, and also handle these scenarios in a consistent and predictable manner. I think I forgot to show you, how it ends at the end of the day. The code is going to be, a straightforward to follow, right? As you can see on the left, you have the verbose code of handling errors manually, and at the end of the day, you have the monadic error handling that is straightforward. It just focuses on the logic. It just focuses on what we want to deliver, not managing these edge cases in a particular way like we used to have, like try except, checking the if, checking if it's a type error, or checking some sort of situation there. So that's what I have for you today. And this is now the right moment for asking some questions. So not sure if you have any. You can do it in Spanish as well, so let me know.
Ahora. Tenemos 12 minutos en esta charla para preguntas, o sea que podéis explayaros un poquito más, pero que sean preguntas, por favor. Levantad la mano los que queráis y os llevamos el micro.
Ok, me escucho. So, lo que pusiste en el ejemplo básicamente usa la librería Result, que por lo que vi está bastante inspirado en Rust. ¿Cómo maneja el tema de los tipos en los errores? Porque puedes querer branchear tu código de error para hacer diferentes acciones en dependencia de qué tipo de error te bit. Eso lo permite Rust. Ahí no sé.
Bueno, este realmente es un grapper, ¿no es cierto? Es una implementación inspirada en Rust. Aquí no tenemos tanta versatilidad en ese sentido. Como viste, podemos anotar el tipo, ¿no es cierto?, del track de success y del track de error como tal, pero no tenemos esa versatilidad de como que implementar algo así de este tipo manual. Se puede hacer con un poquito más de pasos y de steps en caso de que se necesite esa visibilidad, pero no hay nada de momento como que ya construido. O sea, tendremos que implementarlo nosotros por nuestra parte, como un utils tal vez de error handling.
Hola. Hello. As you shown in the example, the result type of error handling is really useful when you have to chain operations, when the output of one function is the input of the next. But in a case where this is not the case, would you say this type of error handling is still useful?
Yeah, this is still useful. We can leverage from other built-in functionalities as mapping, filtering. We can kind of unwrap all the output that it's coming from the success track or even the error. So we have a lot of versatility in this regard. It's just for the example and for the sake of time that I only use the and then, but definitely there are some built-in functionalities that we can leverage from to more complex scenarios and even other type of applications of the result monad.
Thank you.
Hello, I have a good question. Can you use this library in other Python versions where the case statement is not ready?
Yeah, definitely. No, I use the pattern matching example or the match case example just to give you visibility of what you can do with this type of monad, since it's predictable and we have test cases. But you can definitely use it without the matching scenario. Even 3.10 below that doesn't have the pattern matching specification, you can use it right away.
So thank you for the presentation. So for people who have used this kind of facilities in other languages like Haskell and Rust, what do you think are the bits that are harder in Python or that Python is missing to use these patterns?
Well, the first thing is that Python was not created with this kind of concept of monads built into its core. So, you know, you have to depend on this kind of wrappers so you can leverage from this, right? So that's kind of the first thing, because under the hood, if you review the results library code, at the end of the day, it's using the try and accept, but it's giving it less verbosity, right? So it's giving us some composability, also some maintainability, upper hands, and some sort of situation. So I think that that's the main thing that Python is lacking of. Well, not lacking of, but it's kind of on its track, you know, so to have this type of functionality built in. So that's, I think, the main scenario.
Thank you for the presentation. So what about unexpected errors? So it looks nice for expected errors, and you know, I will put the chain of operation in the big try catch block anyway.
Well, if you're training operations and something unexpected rises, you're raising an error, right? That it's going to be handled in the error track of the railway-driven development approach. So basically, having all the chaining operations inside a try and accept is redundant, because it's going to be grabbed in the error, because the error, even if it's unexpected, is going to be catch on that error track, because we are handling on an upper level all the exceptions that might happen, even if it's unexpected, as you mentioned. So that's the versatility and also the type safety that we have in this type of approaches using monads. Yeah, all the chain or all the things that come from the result monad are going to be grabbed into the error, even if it's not as expected as you mentioned. If you are not raising something specifically, it's going to be catched there. So for example, let's say we have a memory leak and we have a memory overflow, and that happens under the hood, we are not expecting that, it's going to be catched on that scenario. So basically you are safe if using this approach.
Hola, Sebastián. Felicidades por la charla. Solo preguntar una cosa sobre vi que se encadenaban funciones, toda la parte de pipes y tal, pero con las funciones asíncronas o la sincronía, porque claro, esos pipes sí se pudieran paralelizar o al menos de forma asíncrona. No sé si hay algo ahí dentro de los monads o algo por ahí.
Tenemos algunos escenarios dentro de sincronía y asincronismo también en el tema de monadas. Para ser sincero, con results, o sea, la implementación en Python, no lo he utilizado con nada síncrono, pero yo esperaría que funcione de la misma manera. O sea, simplemente es como que el paralelismo ahí sería un poquito lo que tendríamos que cuidar, porque tú sabes que son errores inesperados en ese sentido, pero debería funcionar. No lo he probado, experiencia propia, pero debería funcionar.
Hi, hello, Sebastian. Thank you very much for your presentation. It was very nice. I was wondering, last year in PyCon 23, there was another conference, another talk about a software made from a team from Vigo called Meiga that does basically more or less, I think, the same thing as you are explaining today, trying to use functional programming on Python and this error handling. So I was wondering if you have been checked that library, or if you have made any comparison between them, or if you are familiar with this library that is made.
Unfortunately, I haven't done any type of benchmark or performance testing or something like that. So yeah, maybe that's something that I can check, and maybe I came back to you through LinkedIn or something to share some ideas and thoughts. To be honest, I don't have a specific answer for you and that scenario specifically.
Hi, Sebastian. Thank you for the talk. I wanted to ask a more theoretical question, and being most of the languages of data preprocessing and so on going to a more functional way, do you think that this library is another way, another step more to become Python, another functional environment or something like that?
Well, to be honest, I think that that's kind of a personal take and depending of the team that you're working on. So basically, I try to kind of be agnostic related to programming languages and just kind of married to the good practices and good pattern designs. I have found that this is kind of useful for some scenarios. For example, some people used to saw list comprehensions or generators and iterators as a black box that they don't want to use and to just use the kind of classical for loop, but then see the kind of the easiness of using comprehension, right? And that become a pattern. I think that this is kind of the same thing. So you can still use the try except, the if statements and everything for handling this type of errors. But as user, I think it's kind of straightforward to understand the code using this type of alternatives, right? So it's basically a kind of checking, looking deeper into that, be also thoughtful of the scenarios that you are going to be handling. So it's not suited for everything, as I mentioned, because it's kind of a wrapper or an inspiration in Rust, right? It's not built in the Python core functionality. So maybe in some scenarios it's not going to be suitable, but always it's good to have this understanding, right? So maybe it's kind of in depending on the situations, but I think Python versatility helps us to have this type of functional programming paradigms implemented right away and in a straightforward implementation.
We have 2 minutes more, 2 minutos más para preguntas.
Hello. Have you experienced the long chains of operation that can, I don't know, like 20 or 30 or more operations? What do you think about the readiness of that?
Well, you mean chaining a lot of operations consequently?
Yes.
Well, to be honest, that's depending on the scenario. Maybe if you have 20 or 30 operations being chained together in one function, maybe it's time to start splitting it. I haven't done that check personally of having more than, I don't know, 5 or 6 operations consequently because of the kind of the atomicity of the functionalities, right? So no, I haven't encountered the specific scenario or maybe benchmark it to double check if it's as good performance as normal chaining of operations without the library.
No more questions? Okay, so thank you.
Great.